So let's go back to the folder. So if you go to Home, Tools, Plasticity, Applications, Crystal Plasticity, FCC, Random Orientation Block. So Tools, Plasticity, Applications, Crystal Plasticity, FCC, Random Orientation Block. So I'll first remove this results folder here. It's for our previous session. So let's see, what do we ask to do for today? So I ask you to do a more refined mesh and set output step to 1. You don't have to do this. This is basically increase the resolution of the mesh. But with the current CPU power that we have with the virtual machine, I prefer to actually stick to refine factor 0, as I mentioned in task number 3. So you can actually change the loading to uniaxial tension easily by just changing the sign of this boundary condition.txt from negative 0.05 to positive 0.05, and you will get uniaxial tension. So that's very simple. If you have any problem with that, please let me know. For the sake of time, since we're going to cover more advanced features today, I'll just leave it to you. If you have any question with that, please let me know. I mean, user-defined state variables. Yes, you can define state variables and output that value as a part of Quadrature output. And you can, so for all Quadrature points, and you can do that for the whole volume. I'll cover that today, actually. So basically, you should be able to output whatever you want at the Quadrature point. And you should be able to add a few of those to stress strain output.txt, which is basically the average response over the sample. So let me open the PDF first to see the third application. Okay. So now Samuel asked, we have another question just right now from the chat box about what type of information you need for fatigue, as we had yesterday, or any other Quadrature outputs type of data. There is a type of output which is Quadrature output, and we are going to cover that. So if you go, just a quick refresher, if you go here, PRISMS-Plasticity, docs, and PRISMS-Plasticity user manual, it will basically show you, and you can download it. It will give you all the required information for any features we have. So I'll show you how you can actually use this to add any commands. So I've already downloaded that, and it's here. So if you are interested in the output parts, it's here. So it's starting on page 2. And if you just see set right Quadrature output true and copy that and actually paste it in the prm.prm of FCC random orientation block here, then you should be actually write that output for yourself. And then you need to define how frequent you want to output this. So I pick, oh, sorry. This is the doc value. Okay, copy and then paste it here. It doesn't work, so I'll write it. So set, what is it? Set skip Quadrature output step equal to 0. So set skip Quadrature output. Okay, just to make sure that we don't mess it up, let me open up Firefox here in the virtual machine and then go to PRISMS-Plasticity, GitHub, and then open Plasticity GitHub, and then go to Docs, user manual, and download it here. So I'll have that here now. So if you go here for the output part, this is the quadrature output, set skip quadrature output step equal to 0. I copy that and I paste it here, because if you have any misspelling here, it's not going to recognize. And I'll put this every, let's say every 10 step. Make this also 10 steps. So first of all, you can keep this set right output as true to output the PVTU file for you. I'll just disable it. I'm not interested in that right now. I'm just going to output the quadrature output. So back to your question, Samuel, for your case, you need to define exactly the parameters you need for Prisms fatigue that FIPS are calculated, and put this either output steps equal to your half a cycle, so it will print out for you at maximum compression, maximum tension, all of this FIPS information. Or, as I mentioned last time, what you can actually do is you can use set tabular output and set this time basically whenever you want to print it out. So at the maximum compression and maximum tension. That's an alternative. So let me copy and paste it here. So let's say we want to print it out every 10. So it's basically every increment is 0.005. So we want to have it at only the 10th increment. And let's say at 20th increment. So that's basically, you define the time here. So what I did is it will neglect this command when you define the tabular output time. So it will print out the quadrature output for you at this specific times. And basically, since the time step is 0.005, it will be the 10th increment and 20th increment. And I made that false, so it will not print out the PVTU or VTU files. And I saved this. Now, what I actually asked you is just print out for this application the grain ID and position, nothing else. So as I mentioned to you, you need to go back to your folder. There is a source directory in the main folder of Prisms, which is here. If you open source directory, then you go to material model and then crystal plasticity. There is a file update after increment that I mentioned last time, which is the core file for post-processing. So if you see your PDF as well, the address is also here from the current folder actually. So this is the address you need to go. And the source is in the main file. So right now we are there. So I open update after increment.cc with the text editor actually. So if you go to the part that I actually mentioned last time, which is pushback here. So the first pushback will give you the grain ID. So I don't need the phase. I basically comment out this. I don't need the weight, and I don't need to know about the twin information. These three are actually the position of the quadrature point. I don't need the orientation, and I don't need anything else. So what I will do is I will just, let's see if this is working here. Oh, no. So I need to, so you need to comment, but this is something you need to do it just once, because after you do it once, you don't have to basically I'll comment out everything. So you can do that. I typically use Atom I as my editor, so that's much simpler to edit the file. But this virtual machine, I think I don't have it, so I just this part we didn't use enable advanced rate model, so it won't get activated, so I won't actually have to do that. But then I will comment out this as well. Oh, okay. Or another thing is you can actually delete it, but I don't want to delete it because maybe you will. So let's just delete it for now. You should comment it out, but since I don't want to make everything, wait, I'll just delete these lines. So you can either comment out or delete, but it's safe to do the commenting out, but for now you can just delete it. You can get clone the file later. So, and you need to save the file. So basically, let me delete that as well. Okay, basically what it just do is it will just print out for me the location of the quadrature points and the grain ID of those. After you did those changes, then you need to go to your command line here. So let's go to the folder. So CD tools, plasticity, application, crystal plasticity. When you're here, then you need to do make, release, and recompile the code with the new update after increment. So if you hit the enter bottom, you can see it actually starts recompiling update after increment because we already changed that. So in the new recompiling process, it will update, if it will do the update after increment. So this is where it updates the whole PRISMS-Plasticity, and then make that final main executive for you using the new update after increment. So if you go to your previous documentation for training 1, you can see the locations, it start and it end for quadrature output. So whatever variable you want, you're interested, you can just paste it at that region, and for each quadrature point, it will output for you. So now it's finished. So let's go back to FCC and FCC random orientation block. Now, we already asked it to print out the quadrature output for you at the 10th and 20th increment, which will come as 9 and 19 because we start at 0. So let's do MPI run. Let me just double check to see if refine factor is 0 or not. Okay, it's 0. That's fine. So MPI run N2 So now we need to wait like 20 time steps. While we are waiting, just to give you an idea, for prisms fatigue, if you go here, prism center, and prisms fatigue is here. So there is a source folder, and in that there is a material models. This is the most updated update after increment, that if you use this specific update after increment, it will actually print out for you the specific parameters you need for fatigue analysis. So you see here, it just print out plastic shear sleep, normal stress for each sleep. So all the components you required for fatigue. So this is already prepared. You just need to substitute those files with these files and then recompile, and it will generate for you the output that Prisms Fatigue can read. And this is with the rate dependent models, which I will cover today. So let's go back to, so I think the only thing you need to do is essentially you need to define the time here for maximum compression and tension for your Prisms Fatigue output. That's the only thing you need to do. The rest is there. Okay, so 15. So I hope it actually answered your question. So let me see. 16, 17. I think 19 would be the one that. Okay, that's enough. Now, if you go to your folder where it's at tools, plasticity, applications, crystal plasticity, FCC random orientation block, you will see beside stress strain.txt, there are two files, one for t equal to 0.01 and one is t equal to 0.05, 0.1 and 0.05. So let's open one of those. So we actually asked it to just output the grain ID, which is the first column, and the location or position for the quadrature point. So you can see that's what it outputs. And on top of that, how many elements did we have? 5 by 8 by 10. So in total, it's 400. And each element, because the quadrature order is 2, has 8. So it's 3,200 in total quadrature points. So you need to have 3,200, which you have. So that's basically how the quadrature output information works. If you want to add anything else, you can just add to that update after increment and recompile it, and it will output for you whatever you want. And then if you are interested to say, let's say you want to average the stress within the grain with the grain ID of 400, then you can easily write a MATLAB script and post-process this file and say, hey, whatever grain ID is 400 on the first column, then you can average, let's say, sigma 11 over those quadrature points. And that would give you the average sigma 11 over the grain ID of 400. That gives you a lot of flexibility for most of the quantitative analysis you want to have for your crystal plasticity analysis. So let's see. Okay, we did that. And so before I go to the next page, is there any question for this section? For that part? Okay, so I want to give you a hint on another feature that I just mentioned. So there is another feature, as I mentioned, if you want to add a value, a specific parameters, and you want to print it out in a stress-strain.txt file, in which you want to average that parameter. Let's say, for example, you want to add von Mises stress, for example, or some other quantities, and you want to have the average von Mises stress over all quadrature points printed out for you in a stress-strain.txt. So if you go to your doc or manual of PRISMS-Plasticity, basically what you will see is so if you go here for the outputs, there is a part for, so I would highly recommend that if you really want to use PRISMS-Plasticity, at least go over this 21 pages. Just go over it briefly to see what features are available. So this is the output user defined average variable. So you need to copy set output user defined average variable to root. So let me copy this. Oh, okay. And then paste it here. And then you will have number of output average variables 1. So I just, how many variables you want to add? I just want to add 1. So this is the one. Then I need to go to the update after increment. So before I go there, here you can see in the update after increment, I need to find this line, local user defined average output. So I just copy this and then go over this file and Control F and try to find this. Here is the part. You see this part, it says that, let me find it. It should be 1 more. It's actually 0. Okay, this is the part. So here it's that parameter plus 1, plus 0. Let me see how I can make this Control F gone. Okay, so this is the line I'm saying, line 219. Here, if you replace this 0 with any quantity that has been calculated here, it will output the average for you. So for example, let's say we are interested in 1 Mises for that quadrature output. And let's substitute this 0 with the 1 Mises. And then save this. And then let's go back to the code. We need to go to folder before, add the applications crystal plasticity, and then recompile the code because we changed the update after increment. Typically, you need to know what kind of variables for your type of simulation you want to have, and you just have to do it once and then recompile it. And for the rest of your simulations, whatever you're simulating, you don't have to recompile or change anything. These features are supposed to be changed just once before your simulation set, and you recompile it once, and then you can just play around with other parameters. No further need for recompiling. But these are the features which are necessary if someone is really trying to add more output, user defines variables, and okay. So now let's go back to FCC random orientation block. Okay, now let me remove the results folder for now. And then do MPI run -n. And after 2-3 increments, I will kill that. I just want to show you the file. So now, if I open the file, stress-strain.txt within FCC random orientation block, I should have an extra column which is user defined. Here. So this is user defined 0. It's your first user defined. So this is average over the whole sample. So far you can define the local or quadrature point. You can define the visualization. You can define the addition to stress-strain.txt. The only thing I need to cover is the addition to visualization. So what if you want to actually add something to your visualization? The basic visualization features are, as you can see here, the von Mises stress, the von Mises strain, grain ID, and twin fraction. What if you want to visualize sigma 1,1 or sigma 3,3? What should you do? So the best thing is to start to go to the documentation and see user-defined visualization variable. So what you need to do is we just want to add 1. So I copy this. So set output variable 1 equal to true. I copy this and I paste it here. It doesn't matter where in the outputs. So here you show that you actually want to define one visualization and then save this. And as I mentioned in the documentation, you need to find this line in the update after increment. So let's find that one. It's here. So this is, I have a flag there, which is with blue and hard to read most probably, is user-defined variables for visualization outputs, output var1 to output var24. So up to 24 variables, I predicted the user wants to add here. So the first one would be this number 3. And let's say what you want is actually components sigma 1,1. So I will go here. I will copy this T, which is the Cauchy stress tensor, and I will paste here T. Let me see, how can I? Okay, so T. Why the color is so terrible? Sorry. Let me open that with another text editor. This is really terrible coloring. Okay, I will change it and then I will ask you. So T2, 2. So this T22 will be TZZ because in C++ it starts from 0. So 0, 0 is XX, 1, 1 is YY, and 2, 2 is ZZ. So basically this will add to the visualization a ZZ component for you to visualize. You can add anything else, but I just activate one for the demonstration. And I'll save this. And I'll go back to the file. Again, since you're changing the source file, you need to, these are all advanced features. You most probably just deal with them once, but I want to give you an idea of how you can efficiently change those. So while this is recompiling, here, I want to also make this true. So it actually print out the VTU or PVTU for me. And then what I will do is I will go back here. And by the way, since we define output time, it just output this VTU for me based on this time. So I make this a very small value. 2. It's basically 4 time steps. So I need to wait 4 time step for the output procedure. So I save this and I set this correctly. So that should gives me the information I need. Okay, now I will go back to FCC random orientation block. I will just delete this one. Let me close this and close this as well. Okay, and then go here and delete this one. And I will now, oh, did I remove the, okay, that's fine. Let me see. Okay, so plasticity, application, crystal plasticity, FCC, random orientation block. So there should be no results. Okay. And now I will run this. Oh, it's MPI run. And we need only 4 increments or 3 basically because it starts from 0. Okay. I killed this. Now I will go to ParaView. Okay. Okay, now I will open the tools, plasticity, applications, crystal plasticity, FCC random orientation block, results, and project field. And that variable, by the way, since it's calculated at quadrature point, it needs to be projected back to the nodal points, as I mentioned last session. So you need to open this PVTU file and apply. And now, surface with edges, you can actually see the output variable 1 here, which is sigma 33 in our case. So previously, we only had equivalent stress strain, mesh grain ID, and subdomain along solid color. Now this output variable 1 is the stress component ZZ that we define. So this is how you add a variable to your visualization. So now you can modify the quadrature output, you can modify the visualization output, and you can modify the averaged output in stress-strain.txt. So all of this has been provided for users in case they are interested in outputting results besides what we have there as a default option. So let's go back to the PDF file. So is there any questions so far? So this you can do yourself. This is basically just changing the uniaxial file to cyclic loading by making it boundary condition tabular, which is pretty straightforward. Let me know if you try that and you don't get it. It's very straightforward. And this is basically what I just mentioned. How to have, and this line, don't worry about this. This is not These are always changing because the source code is changing, but you need to always look for this part to make sure that you find the correct line. So if you go back, most probably the line is not correct, but the line number, but this is always correct. So this is how I try to find it within that file. With that, let's go one step back and see, as I promised, what if you have your EBSD file and you want to generate the grain ID and orientations for PRISMS-Plasticity. Chris elaborated this a little bit, but let's see from the experimental point of view. What you have is, in your experiment, you have an EBSD file, in which in your EBSD file, you will have, let me show you. If you go to Home, Tools, Plasticity, Training Materials, Preprocessing, and FCC, you will have something like copper data 1 TXT. So let me open this and then I'll answer this. So this is basically a list of orientation file for each voxel that you would get from EBSD. And then for our application for Dream 3D to read in that file, you need to have 2 columns with 2 number 1, because all of the pixels in that EBSD has the same value or weight. So I'm using the unit here. And then that would be the input file for Dream 3D. So this part is from your EBSD map for each voxel. And then you need to also have the number of lines here with these keywords. It should be exactly like this. Any other formats or minor changes cannot be read by Dream 3D. So angle count, semicolon or column 399. 399. So that's the number of lines you have actually here. So if you go here, you would have 400, which the first line is the header line. So that's, you need to prepare your EBSD file with the format like this. Let me see, what's the question? Is it possible to perform a stress control cyclic deformation? Yes, it's possible. If you go to the documentation, there is a boundary condition which is called Newman boundary condition, tabular Newman. So it will apply homogeneous traction on one side. So you can fix it with boundary condition, with simple boundary condition on one side, and then apply a Newman boundary condition on the other side. And then you can figure this out on, here should be nodal torsion, and this is here. You can read in this part tabular Newman boundary condition, and then you can apply this boundary condition that you need. So where I was? Okay, so I was explaining the input file sample you have here, which is copper data 1. So first, you need to do one pre-processing step for your EBSD data map. So now you have your EBSD data map ready. So then you need to open your Dream 3D. So all of the steps that I'm covering here are explained here. So you can just follow the PDFs, basically. So this is, first you need to open from PRISMS Tools, Plasticity, Training Materials, Preprocessing, FCC, and there is a JSON file, which is the pipeline we have for PRISMS. If you open that, you need to change some features. First, you need to check the crystal structure, so it's cubic, that's correct. Then you need to go to ODF and click on bulk load from file. And then select that copper. Okay, go to Prisms Tools, Plasticity, Training Material, Preprocessing, FCC, that copper data 1.txt. And select that and click on Load Data and then Create Data. Okay, now you have all the information inputted. Now, after you have that, you need to update bunch of addresses here. So here, if you go to pipeline 8, you need to select this. You need to just say save. This update the address here. And then you have right Dream 3D. You need to update that as well. Select, save, yes. And then there is another one, export ASC data. Select, choose. So now you have everything. So 3 locations, number 8, number 9, and number 17. Basically, any place with the export or write. That's places you need to select the address and just click select. It's a very simple. You need to direct it to the correct directory. And then you can say start pipeline. It will generate for you the microstructure based on the EBSD file you have. And it will capture the correct statistics. So whatever other changes you want to make your Dream 3D, you can change this pre-defined pipeline, and that would work. So we'll wait until it finishes. So the output should actually come in the same folder as we have that copper data.txt one. So if you go to here, the outputs are all here. So now you can actually open with the ParaView the macrostructure you just generated. So, and these 2 files, grainid.txt and orientation, has been created for you. So if you open the grainid.txt, it's a 32 by 32 by 32 microstructure that has been defined actually here. 32 by 32 by 32. And, oh, sorry. So this has about 20 lines of header. So you need to know the number of header lines, you need to know how many voxels in each direction, and you need to know the name of the file. That's all you need. And if you go back and open the orientation file, it's pretty much the first line doesn't matter and the rest of them are Rodriguez vectors. So it will automatically for you generated the correct inputs for PRISMS-Plasticity. And then you can also open with the ParaView the macrostructure you have from Dream 3D. So if you open the ParaView, you can say open tools, plasticity, training, preprocessing, FCC, and copper XDMF, and apply, and then make it feature IDs or grain IDs. This is surface with edges. Or you can just do surface to make a cleaner look. So this is the macrostructure. You can increase the resolution or whatever you are interested in. This is, I just make it a little bit coarse to run Dream 3D faster. So this is the macrostructure I just generated. So what I would like to do is I would like to use this macrostructure which I generated in one of my simulations, but be careful since this macrostructure is 32 by 32 by 32 and we are on the virtual machine, you have to use lower resolution for your FEMesh. But let's try to do this, see if our memory of virtual machine can handle this macrostructure. So let me check on the PDF to see we are on the right track. So here we generated it. Update the addresses, okay. Number 8, number 9, and number 17, as I mentioned. 2 outputs will be grain ID and orientations. So this is the grain ID. And okay, so what we are going to do next is we are going to use rate-dependent models. So if you see this page of, and we are going to use rate-dependent, so we are going to change that file to rate-dependent and see how we can go from there. So for that, as I mentioned here, if you go to your source file, let me show you here. You go to Home, Tools, Plasticity, Source File, Material Models, Crystal Plasticity. There is a Material Models library here for you. One of them is rate-dependent model. So in the rate-dependent model, there are 2 files. You need to copy these 2 files and then paste them back inside this folder to replace the original ones. Replace. So now, if you open the calculate plasticity.cc, which is kind of main constitutive model integration file, you'll see this is the, oh no, that was the wrong file. Calculate plasticity.cc. See, it says this is the rate-dependent crystal plasticity model. So we are in the right file. Now, since you are changing the source file, you need to recompile this. And now you should see the calculate plasticity. Oh, no. So just one note. You see here, when I did the make release, nothing has changed. So it means that our change has not been recognized. So the clean version of doing recompiling is actually you remove any CMake folder and start from the original folder, which is actually 2 folders before this. But I have a very short trick to handle that. I mean, you can go with the clean way of doing it, which is basically you need to remove this file, and you need to go 2 folders before this, and you need to remove this file, not that file, this file, any file which has been created by make. But that will take some time. So instead of that, what I will do is I will go back here. I will remove this file and user function, these 2 files that I just copied. If I remove these 2 files and then I try to do, let's go back to the folder application, crystal plasticity, do make release, it will give me an error. Why? Because there are 2 files which has been removed from the file. So you see there is an error. Now, if you go back and copy it again, it will recognize them. That's a short trick, but you don't have to do that. You can do the clean version. So now if you go back to this and do make release, it will start recognizing the new files. You can see that. No, it didn't actually. Okay, how can we do? Okay, let's try to remove these CMake files and see if it works. I hope it doesn't ask us to go to the main folder. So I remove this CMake file. Oh. Since it's folder, you need to say remove -R, and you need to remove the CMake cache. Let's see what else. Remove main file and remove this make file. So the only file you need to have, oh, you also need to remove the CMake. So the only two files which should be remain is CMake list.txt and main.cc. So now if you do make release, you need to do CMake first. CMake dot. So you need to do first CMake dot, and then you need to do make release. So two commands after you cleaned up the directory. Typically, if you remove the file and recompile it, it should work, but I don't know, this virtual machine, slightly different from what I used to. So now it will, okay. So let me just try very quickly to see if it actually reads in the rate dependent models or not. So let me try one of these rate dependent folders. You don't have to follow this. I'm just trying to see if this works or not. If this doesn't work, we need to go back and recompile PRISMS-Plasticity after. Okay, so this is rate dependent. So let me do MPI run. Oh no, it's working. So we're good. So this is working. And so now, let me go back to the PDF. We have already generated the macrostructure. So we will copy the macrostructures that we generated to this folder. FCC random rate dependent. So how can we do that? You can do here, you can actually go to plasticity trainings, training, pre-processing, FCC. You generated this grain ID and orientation.txt. So you need to copy these two files and then paste it inside applications, crystal plasticity, FCC random rate dependent. Replace. And I will delete this grain ID file because this doesn't matter. Now you need to, let me delete this one as well. So now you need to open the prm.prm. Okay, so you need to change a few of those lines. Let me see what was my recommendation. So change it to 16 by 16 by 16. So first of all, the mesh, we like to have it 16 by 16 by 16. So the first change is set subdivisions 16 by 16 by 16. The second, we want to have an output, so true. And then we want to print it out every 5 increments because this is a huge simulation for the virtual machine and we don't want to wait that long. And then let's say we want to have the, let me see, what are the other recommendations? Delta T equal to 0.005. So 0.05, and then total time t equal to 5. So I will change that as well. Okay. Now we have everything. So, okay. There are a few lines here that I will explain momentarily. Let me see if it actually, okay. So it will be on the next page. So before I start explaining this, the last 3 lines, we changed the grain ID. So that 5 by 8 by 10, as I mentioned last time, it was a very idealized way of crystal plasticity, which is each element is a grain ID, and that's like just for maybe a stress strain curve. So now we have a 32 by 32 by 32 that we generated, and the name of that file is actually different now. The name of the file is grainid.txt. So let me rename this, copy the name, and paste it here. And the number of headers are now 20. If you see here, open this, see there are 20 lines header. So the last part is we don't want any quadrature output, so that's false. And it's orientations.txt. So we are set. The only part I need to explain is what are the changes for, and this can be 0 actually. And this can be 0 as well. So what are these for crystal plasticity find element rate dependent model? So if you open the PDF, we update the mesh, we update the output, we update the time increment, we update the microstructure information in the PRM.PRM. So what is the rate dependent model? In the rate dependent model, there is a flow rule, which is this. So there are a few parameters. So set material constant 1, which is this line. These are corresponding to any of those from this formulation. So when I put everything 0 here, it means that there is no back stress. Okay. And the rest of that is basically gamma dot node, which is the reference shearing stress, shearing rate. M is the sensitivity to rate dependency. And these 4 numbers, we basically integrate the rate dependent crystal plasticity model within 2 loops, that in those 2 loops, there are a maximum number of iteration and maximum threshold to be satisfied to numerically integrate this rate dependent model. So these numbers are pretty conservative, so you can stick to those numbers. And or you can, I mean, sometimes I just want to be safe, so I make it a 10 to the power minus 6. But the lower you go, the longer it will take for the rate dependent model to be integrated. And this is the maximum number of iterations for that loop. And you remember someone asked me about state variables. You can add new state variables besides the one we have already placed, but you need to add to this number and predefine the initial value for those state variables. Within the, so basically the rate dependent model has been implemented in PRISMS-Plasticity using a feature which is for defining new constitutive model for PRISMS-Plasticity. So you have new material, user defined material constant, and you have user-defined state variables. So if you want to know more about that, in the paper of Prisms Fatigue, we have actually gone over the way it has been numerically integrated. So you can read that, and you can come back to me with questions. Okay. Yes, the correct file is calculateplasticity.cc, but I will cover that momentarily, where you can find more data about that. So far, we have done all the changes we need. Let me see here. Okay, so before I go here, I will start running this simulation to just show you how would be the macrostructure look like. So I will go to random rate dependent, which let me say, okay, so it has been already saved. And we have this, let me open this also to make sure that. Okay, so this is the right file. So what I will do is I will try to run this with 4 processors and see how fast it will become. Hopefully we won't face memory issues. Sometimes we will. Okay, this is running. So now you see it's 16 by 16 by 16 elements. So it's like 4,000 elements, 96. And it will run until increment number 5, which since it starts from 0, it will be increment 4. And I will kill the simulation and post-process the results to show you how the input macrostructure you read in would work. Before it comes up, is this model capable of capturing size effect? Yes, you can. So we have implemented a size effect with that, but the size effect that we implemented is through modifying the CRSS. So you can basically modify the CRSS based on the size, and you can input the size with the orientations.txt as an additional voxel information. But we don't have yet released the strength gradient model that we are trying to develop. That will be the next year release, I think. So I will kill that. So we have like 2 papers coming out. 1 paper has been already accepted. So you can go over the detail for effect of grain size. It can actually capture the effect of grain shape as well. The next paper hopefully will be out soon as well. So there are 2 papers using PRISMS-Plasticity for grain size effects, and you can find more details on that. So let me open the, okay, sure. Let me open the ParaView. Open, we'll go to Home, Tools, Plasticity, Applications, Crystal Plasticity, FCC, FCC random rate dependent, results, solution PVTU, and project field PVTU, and apply. Oh, because the size is different, I think. How can I make that? Okay, that's working. So you can see actually the equivalent strain or grain ID here. So see, that macrostructure is the macrostructure we generated with Dream 3D, except we are modeling that using 16 by 16 by 16 elements. So that's lower resolution compared to Microstructure. So if you model that with 32 by 32 by 32, you will exactly mimic the same resolution. And then here you only have this, but as I mentioned, you can add anything else you want as an extra information. So just as the last question, or the one before the last one, I want to address, if you have any other new model and you want to implement that, where should you look for? So the only files you need to update for adding your own crystal plasticity model are calculate-plasticity.cc and user-functions.cc. And basically calculate-plasticity.cc is the main implementation, but the beauty of it is this user-functions.cc, you can add any auxiliary function you need for your implementation, and you can easily add it to that user-functions.cc and read it in that function, so it doesn't make your implementation messy, adding additional functions. So you can add all the functions here and just have the main function here. And if you go over this documentation, which is user-defined material model manual.pdf. So let me show you here. If you go to PRISMS-Plasticity documentations, user-defined material model manual. This is the file actually defining what are the all variables you have. And you can read over this and hopefully get an idea about how you can model your new constitutive model. But the best way is reading this, reading PRISM's fatigue implementation, checking the rate-dependent implementation, and then compare this together, and you would clearly understand how would the code works. And if you have any further question, I would be more than happy if you can reach out to me. I will guide you through the process. So this is where you should look for that. And okay, so the next application I want to go over is periodic boundary condition. So is there any question before I went to periodic boundary condition? Okay, there is one question. No, the TIE 64. So TIE 64, if you just model it as an HCP, you can do that. But if you want to have a like homogenized version of having both phases, no, we didn't release it. Okay. So periodic boundary condition. So periodic boundary condition, it's very tricky to implement that even in commercial softwares, because you have this multi place constraints. You have to set up a lot of constraints to actually implement efficiently the periodic boundary condition. The reference that I put here has thoroughly gone over that periodic boundary condition, but for majority of the applications, you just need to read this once to get to understand it briefly. The rest of the files, you can just use the whatever we have, because there are two famous cases: fully periodic or periodic in two direction and then free surface in one. For both of these cases, we have already pre-generated the constraints. So you just need to copy that. And so the only thing you most probably need to change is the loading part. And if you actually go to the files here, the folders and you go one step above, you will see there is a periodic boundary condition somewhere here. And there are a few types of loading. So you can just see how did we apply pure shear, simple shear, cyclic, uniaxial tension. And then compare this with each other and understand how you can apply different loadings. But I will go over some of the files quickly to just give you an idea about what are the usage for those files. So just to give you an idea, there are some notations borrowing from this dissertation to apply this constraints for periodic boundary condition. So we have, for applying boundary condition, you have three different group sets of degrees of freedom: vertices, faces, and edges. And each of them has a symbol, as you can see here. So you need to go over where is where and what is, for example, FXP, which is face nodes excluding the edges and vertices for surface normal to x-axis at x equal to h, which is the maximum length of the sample for a cubic sample. So you need to go over this to understand the nomenclature of this periodic boundary condition, which is based on the reference I just showed you. So in the input file, if you open, let's say, let me open one of those. Let's say periodic boundary condition cyclic tabular. This is actually what we use for most of our fatigue applications. So this file specifically is not reduced integration as we use for most of our fatigue application. This is full integration. For reduced integration, you need to make this 2 equal to 1. So one important point is whatever input file we use for the publications of PRISMS-Plasticity or fatigue, there is a link at the end of the paper which direct you to some materials commons folder, which include all the input files which generate the exact outputs for that paper. So if you are interested in any of those results or inputs, just look for it at the end of that manuscript and you find the data availability, and then you can look for it and check the prm.prm files for different applications. And you can go over it and see what are the state variables we are using. But that's enough for now. So subdivisions. So I just want to make it 4 by 4 by 4 to make it very quick, because these periodic boundary conditions are more costly compared to regular simulations. So the next step is, if you see here, it says set use simple boundary condition equal to false. And then set use periodic boundary conditions equal to true. The next part is the file which include periodic boundary conditions constraints.txt. And there are 3 numbers for faces, edges, and vertices. If you see in the PDF that I shared, I actually completely explained what are each of those files are. So I would just skip that. Please go over it. And if you have any questions, please feel free to reach out to me. This explains what are each of those files mean. But the good thing is, for the specific type of boundary condition, you don't have to change these files. These are already prepared for you. For example, in the case of fully periodic, this file is already provided in the folder. So if you just open it, periodic boundary condition constraint, you see all of that has been provided for you already. So you can just directly use it. So you don't have to understand more about these files. It's just good to know what each of these means in case you want to understand how we implemented that. So if you go here, this, oh, in case you have fully periodic, these numbers should be like this, 12, 27, and 9. But if you have two sides periodic, one direction free surface, you need to have 12, 14, and 6. And that file that I showed you, it should be updated. Where can you find updated file for free surface? On Materials Commons from the link provided for PRISMS fatigue paper. For example, let me show you. So if you go here, if you say PRISMS fatigue, there will be the link to the publication, and then there is a data availability. And the data availability, there is a Materials Commons DOI. You click on that. And then there are files here. You can use in Globus. That's much easier if you have access, or you can go over file or zip file. I'll try to open the Globus. So free surface effect, that's a section in that paper. If you open that, we have files, simulation files. Sometimes this doesn't work. Okay, let me go here from the files. Okay, free surface effect, simulation files, and then there is a periodic boundary condition constraint.txt. Now, if you look at this, this is actually different from what we have here. I didn't open it. So for example, if you go all the way down, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 line, which is for 9 constraints you have here. But if you go for the other file, it should be 12. Let me check to make sure if I have it correct. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is for when you have one free surface. So actually you can get all the database for that publications by going to these files, and all the sections are here. So that's all you need to have for that simulations. Sometimes because belong to the older version, you need to use the older version to run this, or there is just a little tweak to make this work for the newer version. So if you face any problem or issue, feel free to send me an email. It's definitely something very quick and solvable. So you have access to that, all of those input files for the manuscript. So let's go back here. So this is how you define. So this is not going to change for a specific boundary condition. So for fully periodic, this is always 12, 27, 9. But the real change starts from here. So this is where you actually define your loading condition for different vertices. That you can also copy from that dissertation that I mentioned. And if a degree of freedom is constrained, you put the value 1 on that line. If it's not, you leave 0 here. And the amount you're applying at the end of simulation or at the end of cycle is defined with the value here. So that can be also obtained from here. So if you go here to, let's say uniaxial cyclic, you understand what type of loading is applied here. If you go uniaxial tension, then you can understand that. So eventually that would give you the required input file for that type of simulation. So please go over all of those. It seems a little bit complicated, but I'm pretty sure you would get a really good feeling after reading all those notations. And it has been thoroughly explained in this PDF as well. So for example, if you want to apply tabular periodic boundary condition like cyclic, then you need to define the first half cycle total time, which is in case 10, and then you define the amount of deformation for that half a cycle. And that would explain how would it apply the cyclic loading using this periodic boundary condition. So it has a lot of information, but you can try that. You can also change those information. So let's do something interesting. Let's modify one of the input files we have in that folder. Okay. For that, this is the periodic boundary conditions. First of all, this is using rate independent. For example, you want to change one of these for the fatigue application. So first of all, you need to make it rate dependent. So I will open this uniaxial cyclic tabular, and I will do, let's say, I think 16 by 16 by 16 would be too much for this virtual machine. So I will use 8 by 8 by 8. Hopefully that's not too much. And then what I'm going to do is I'm going to copy the microstructure I just generated by Dream 3D, or a microstructure that I copied from the paper. So let's do that actually. I can actually, oh no, let's stick to this for now. It's easier. It doesn't matter. You can just copy it from the paper and replicate that figure. Let me do that for you. Okay, so let me do prisms fatigue. This is just to show you how you can actually produce that files. So there is a data availability. There is a DOI here. Files. Let's go grain morphology effect because this is fully periodic. And then let's say random elongated periodic. And I want to have grain ID. Okay, so I will just copy this grain ID. And I want the orientation. And I will download this file. And I will download this as well. Open the folder. So these two files, I will just copy them. Going to home, tools, plasticity, application, crystal plasticity, FCC, periodic boundary condition, and I will paste them. So first open this grain ID underline 0.txt. So we have like 20 lines and it's 29 by 29 by 29. I will just do this with the smaller number of FE mesh, but in the real CPFE simulation of what we actually did, that was a 29 by 29 by 29 simulation. So let me go back to this. I will use 8 by 8 by 8, but then I need to go back here and make this 29. You need to update the input microstructure, 29. And the name of the file, now it's grain ID dot underline 0. So I will copy and paste it here. And the number of header lines are 20. And the name of the orientation file has been also changed. It's orientation underline 0. So I will paste that as well. Okay. So now we need to change some of this information. So if you go back to the link that I just brought it up from the materials common and go to files, we did, oh no, I went one. Okay, so this is grain morphology effect. So if I open simulation file, I need to copy some of the information from PRM0.PRM. So you see, this is the actual file we used for PRISMS fatigue paper, but I just want to copy the rate dependent part and the, so you see here, you remember I mentioned you that this is when you actually apply, print out the simulation output at the specific maximum compression and maximum tension. This is how you define it. So let me copy this actually. And paste it here. And make this true. So we want the PVTU file output, but the problem is we cannot wait this long for simulation to be finished on the virtual machine. So I will just change this to a few time steps. And then let me go back here to see the boundary conditions that we are applying. So I will copy this. And I will paste it here. And then the time step is here. Okay. So see, rather than waiting 0.7 to print out the time step for maximum compression, what I will do is I will change this to 0.05. So I just need 5 increments to output. So that would not be the maximum compression or maximum tension. That would just be some part of during uniaxial compression, for example, for periodic boundary conditions. So the only change we have made compared to real PRISMS fatigue manuscript is A, the number of, oh, there is another change. So you can see here that we use the reduced integration. So the only change we have here is, let me actually use reduced integration as well here. Okay, so now we use reduced integration. The only change is A, we are using 8 by 8 by 8 rather than 29 by 20 by 29 because of the computational time. And rather than outputting at maximum compression, maximum tension, and maximum compression, we just output after a few increments. So that's the only change compared to the real results of that paper. And we need to also change the size because we copied the boundary condition and it applies based on the real size of that file. So now you need to go and copy this into this. Okay, so you see the size of the sample is 0.0725. So let me do calculator. And the amount that you're applying is 0.005075 dividing by the size of the sample, which is times 100, 0.7%. That's what we did for our fatigue application. So loading 0.7% like periodically. So that's how we did apply that boundary condition. And then let me see what else. We changed this. Oh, the next part is the material properties. So we need to copy the material properties as well because this is rate dependent model. So let me copy the information here all the way to here. Okay. So now you see here, this is the exact parameters that we use for fatigue application for PRISMS-Plasticity paper. And what else? Sometimes we are adding extra state variable. So for example, you can see here, depending on the number of slip system, so this has been designed for 12 slip system, or we have like a twin dummy slip system. So we actually have 13 for 12 slip system if we don't have any twin. So the error that typically people get, and they need to be worried about it, is the number of state variables is actually a function of number of plastic slip systems. So something that I would suggest is, if you don't know how many state variable you actually have, there are two ways. An easy way is you can just add extra until you don't get the error, or you can go here, here to, let's open the other ones. Source file, material model, crystal plasticity, and open actually this calculate plasticity.cc, and see within this file, there is a part that it's talking about state variable. So the maximum number of state variable we have is here. It's 4 times number of total slip system, which in FCC it's 12, but as I mentioned, if we don't have any twinning, we always have one dummy twin system, which becomes, in total, it becomes 13. So 4 times 13, which is 52. And then we have dimension time dimension, which is 3 by 3, which is 9. And it starts from 0 in C++, so it's always +1. So you need to have 62 state variables for FCC system with the current structure of rate-dependent model. If you change the model and increase the state variables, the only thing you need to do is you need to increase that state variable number here inside your PRM uniaxial cyclic tabular, wherever you have. So 62 now is correct. So the user parameters for rate dependent is set based on what we have in the paper. And the elastic modulus is set. The latent hardening ratio, I believe it's set. It doesn't matter for that material. And this is the input file. So I think this is all we need to do. Let me double check it. Yep, that's correct. So the safest way, I just did all these changes because I wanted to show you which parts are important. But the safest thing to do is actually get the whole simulation file package from the materials common and start simulation on that folder rather than modifying another folder. That could become a little bit messy. So now let's go to the folder that we just made in, where was it? Periodic boundary condition. Okay, it's here. And this is the file that I think I modified. It's PRM uniaxial cyclic. So it would be MPI run. I will use 4 processors just to see how it goes. And then uniaxial cyclic tabular. Oh, that was a bad mistake. Cyclic. Okay, this should work. We changed a lot. Let's see if it works or not. Okay, so I mean, this is faster than what I expected, but it's good. Okay, after 5 increments, you can see it write out the outputs. And it actually used the microstructure, but we are using the Corsair mesh, which is 8 by 8 by 8, which is 512. Yes. And then you can see here periodic phase pairs 192. And this is for periodic boundary condition, and everything else is set. So now let's go back to ParaView. Let me delete this one. Actually, you know what? Let's try, now that this is this quick, let's try to do that 29 by 29 by 29. See if the virtual machine memory would help, can capture this, and just do 2 increments. Okay. And then try to rerun that. See if it can handle it. Oh, it actually ran. Okay, that's good. It will take some time to generate 2 increments because this is like the real microstructure. Using virtual machine is not a good idea, but I think it will eventually go there. Let me answer some questions here. It's safe to assume that the code runs relatively fast as first because it's solving the elastic part of it. That's correct. That's exactly correct. The initial increments are, since it's elastic, you remember that loop that I mentioned to integrate the rate dependent part, which has 2 inside loops and it has critical threshold and number of iterations, that will converge faster for the elastic parts. That's a really good statement. That's true. I can answer another question before we reach to the second increment if you have any. Okay. I think I didn't plan to do this, but I think this was nicer. Now you can actually go and find the real simulation files and try to start from there. That's much nicer. I think that would help you a lot. The majority of the files or the publications that are out, you can just go and find the input files and see what did we use. So you can just read the input file and understand. But I just want to reiterate, read the documentation, read the user-defined material documentation, read the source file, especially update after increment and calculate plasticity. Those two files are very important. Will give you a lot of idea about how this will work. And then if you have any question regarding those two files, please come back to me. I'll try to explain. Put the question inside the Google group, so when I answer that, other people can also use the information. But if you understand pretty much these files and those documentations, I think you have a really good grasp of PRISM's plasticity. And you can always use those input files we shared in Materials Commons for our publications. So that will cover a lot of ground that you would have for fatigue or plasticity. We will need to wait 2 more iterations. Okay, we're almost there. Now, interestingly, it will also generate the quadrature output the way Prism's fatigue wants, or not, because you know what? We didn't copy the update after increment from Prism's plasticity. It's actually just printing out now the grain ID and their locations of the quadrature points. So that would be different. So you need to copy that update after increment from Prism's fatigue and paste it and recompile it. So that would be it. So let me clean this. Could you share how to model notch or porosity? That will come out very soon. Hopefully, we have a paper in revision, which hopefully will be out in a month, and we will share a whole materials commons database that you can model different notches, even random free surfaces. That's really cool. So we will share that hopefully within 2 months. So let me open the power view, go up. Sure. The periodic boundary condition results. Okay, so you see, first of all, we have a quadrature output that I will open later, but let's open the PVTU file. And let's open the solution PVTU as well. So that was the microstructure that Dream 3D generated basically for that microstructure. And if you open the quadrature output as well, Let me open the Quadrature output. Where should we look? Okay. Applications, crystal plasticity, FCC, periodic boundary condition. So this is the Quadrature output. You see, because we already changed the user update after increment to just print out grain ID and the locations, that's the only information which is provided. So if you actually copy and paste the user update after increment from the Prisms fatigue here, this file, you would get the required outputs for fatigue applications. So that's the way you should go. So the only remaining application that I want to briefly mention is the advanced twin model. So I will just briefly go over that. The changes you need to make is super simple. So we have a new advanced twin-D twin model, which can capture both parent twin and children at the same time. So the way to use, this is the application we have inside the sample. So in order to use that, you need to first copy the rate-independent advanced twin model, calculate plasticity to the user file. So let me try to see if it works quickly. I'll try to cover this as well. So if you go to, this is the plasticity folder. So if you go to source, materials, crystal plasticity, and then go to material models, and there is a rate-dependent advanced twin model. So if you look at this, there is a calculate plasticity that if you open that, this is how it looked like. There's another way to go there, is if you open the folder, plasticity, go to source, material models, crystal plasticity, material models library, rate independent advanced twin model, and then you can actually copy and paste it the same way you change the so if you now open the calculate plasticity, you would see the no, that's not working. Let me go over here. Rate independent. Okay, this is correct. So I'll just need to copy this, go up and paste it here and replace it. And then try to refresh this and then calculate plasticity. And this is correct now. So now, sometimes you see that the recompiling feature doesn't work, but let's see if it works now. I will go back to applications, crystal plasticity, and recompile the code because we changed the source file. Will come, and that would basically be, if you have any questions, general question, I'll try to direct you to the right options, and I'll try to cover your questions basically and show you what would be the best approach for that cover. So let me see if you have any questions, quick questions now, but if you have like more major question, Friday would be a good place for asking that.